So this subject is completely linked with physical metallurgy. Right? So that's why you can watch the YouTube videos on this physical metallurgy if you want. Because if you have any doubts related to physical metallurgy, then you're not able to understand this one also. Right? Anyway, so during this course, I'll teach you some physical metallurgy concepts also, which is related to this subject, right? To make it easy. And let me tell you some important points. This subject is also very much important for placement. Mineral processing may not be important. Not sure, maybe. Like INACUL, if INACUL is coming, that is related to mineral processing, so they may ask. But if Vedanta is coming, if Hindalco is going to come, if Tata Steel, JSW, JSPL, they will going to ask you physical metallurgy and heat treatment, mostly. They are interlinked with each other. Right? And you will get questions in the GATE exam also. Like maybe 10% questions will be there, maybe 30% question will be there related to physical, phase transformation and heat treatment. These are the three subjects which are linked. Physical metallurgy, heat treatment and phase transmission. All are linked together. So 30% question will be coming from that part. These three subjects. Okay, fine. Anyway, so the first content is material tetrahedron. Okay, how many of you can answer it? I think few of you can easily answer it. Okay, please raise your hand. Material tetrahedron. Who was taking your subject? Maybe Mandla ma'am, right? HOD sir. Okay. Can you answer it? Material tetrahedron. Okay, what is the meaning of tetra? Tetra means four. Hedron means faces. Fine. So that is not linked to this, but anyway, tetra means four. Hedron means faces. So if you draw a tetrahedron, for example, can you draw it quickly? Tetrahedron. Fine. You can draw it straight also. So if you carefully look, there are how many points? Basically 4 points. So if I can write here. Okay, anyways, let me discuss, then I will come to that. So whenever we will go to buy any product, for example, let it be any metal piece, for example, or any product related to any metal or alloy. So what you will ask to the shopkeeper? Give me that particular product which is durable, which is stronger, for example, which is shiny, which is resistant to corrosion, right? So that means at the end you will ask a material which have high performance, okay? Which have high performance, which will give you high performance. Even if you will buy a scooty or a car, you definitely people ask what is the mileage it will give. So that is actually related to performance again, okay? Related to performance. So my point is, at the end, whatever we are doing to get high performance, okay? High performance material, right? So performance may be good, may be poor, or it may be very high, very good, or very high, good performance, if you can say. But this performance depends upon property of the material. That is the part we are going to discuss. So performance will be affected by property. That means if you change the property, the performance will change. This is the relation. This is the most important relation, right? Then how property is related to other things. So property is related to structure. Since we are metallurgical engineers, we basically check what? Either we will check the microstructure or we will detect the crystal structures, right? Crystal structure will be detected by XRD, by doing X-ray analysis, X-ray diffraction analysis. There is a particular characterization called XRD where they will fall X-ray on it and they can find out what are the different phase in that. Different phase means what are the different crystal structure, okay? But if you want to know the microstructure, then you have to look into microscopes. It may be optical, it may be electron microscope. Basically in our lab we have optical microscope. So what is the difference between optical and electrical or electron microscope? What is the difference? Electron gun, yeah, somebody is saying. Actually in optical microscope we use visible light, right? So visible light will allow to fall on the sample and it will reflect back and you can able to see the structures, right? But in case of electron microscope, we are using electrons. Electron as a source, not our visible light. So what is the advantage? You will get very high magnification by using electron microscope. Magnification means you can blow up something. If it is very small, you can able to see the big image by blowing it up. It will magnify. Fine. And second one is resolution. The electron microscope have very high resolution compared to optical. So these are the main two important points you have to remember. There is the major difference. Electron microscope have high resolution, high magnifying power. But optical microscope have some limitations. You cannot go. What is the why this is so? Can you tell me just from backside why optical microscope have low resolution and low magnifying power or something? Low resolution. Resolution is more important. What is the meaning of resolution in simple terms? Can you tell me? Magnification you understand. If something is smaller, you can blow it up and you can see a bigger image of it. You magnify many times depending on objectives and eyepiece. Fine. Or number of lenses, if you are going to use more and more, you can magnify more. Resolution means what exactly? Yeah, in simple terms. Clarity. Clarity. Okay, clarity. Clarity in the sense, okay, yeah, somewhat correct, not exactly. Resolution means if some features are very small, they are also very close to one another. You cannot distinguish which one is what. They will appear as a single object. Suppose I have these two pens, for example. I have these two pens. I'll keep these two pens together. These are two different objects. But they are placed so close to one another, the person who is at the back cannot distinguish. He will think that this is a single piece. This is not one, this is not one. He will think this is a single piece of object. Right? Resolution means even if he is sitting at the back, he can easily resolve that this is one component, this is another component. Even if they are placed so close to one another. Right? That is called resolution. You understand in simple terms. So basically, if you understand that we are talking about microstructures mostly, microstructures. Microstructure means those structures whose size is below or nearly how much? 10 to the power minus micron. Minus 6. Nearly. So the very small, that means very small. Now Armstrong is atomic level. So that means if the size is so small and they are so close to one another, how you can able to see them? You cannot able to see them by optical microscope. You have to use the electron microscope. Right? So this is called resolution. It is clear or shall I tell you again? Resolution you understood? You can easily distinguish two different objects if they are placed so close to one another if the microscope have good resolution. Okay. Anyways, we will not go into that. So I told our main important point is we need good performance material, and good performance material will depend upon properties. What is the property of that material? And properties will be affected by microstructure or crystal structure. These are two important points you have to remember. Either crystal structure will affect the property or your microstructure will affect the property. I can give some example, we will discuss that. And finally, the most important point, the process. Very good. The process will decide what will be the microstructure or what will be the crystal structure. If the material is showing different crystal structure at different temperature, different condition, then like steel, for example. Steel always show different crystal structures, right? You know, iron also shows. Some kind of aluminium alloys also shows that. Fine. Is it okay? So in that condition, if you change the process, you can change the crystal structure. Or if you change the process, you can modify the microstructure also. Can you give me an example of microstructure from the behind? Okay, let me ask from that side. Yeah. You. Can you give an example of microstructure? I'm asking you. Yeah, yes. Just give an example of microstructure. You have attended the physical metallurgy lab also, right? Class and lab, no? At least from the lab, can you tell me what microstructure we have seen? Okay, sit down. You? Can you answer? You may be wrong. I don't have any issue. perlite you have seen, okay. Fine. Perlite, fine. Yes, Satyajit, can you give an example, simple example? Perlite, okay. You're right. Martensite you are able to, okay, you can able to see under optical microscope. Is it possible? Austenite? Austenite, okay, yeah, it's possible. Okay, fine. Yeah, they are right, austenite, perlites and all. But those are what exactly? Those are, like perlite is a mixture of phase. As he told, austenite is a phase. So that means if you can able to change the phase from austenite to ferrite or ferrite to austenite also, you can change the property. Fine. Is it okay? So finally, metal tetrahedron, what I can write? I can write here processing. Fine. This time I can write, for example, what I can write? Structure. Then I can write property here, and I can write from the back side. If you want to remember, it is easy, because always we want good performance material, and good performance material depend upon the properties of the material. Properties of the material is affected by your structure, and structure will be affected by the processing, because we have different kind of processing. Okay, can you people tell me, just I want from you only, whenever we are dealing with metals, alloys, what kind of synthesis process we are using basically? You want to synthesize a particular steel or aluminium or an alloy of aluminium or steel. What kind of synthesis or processing we are doing basically? Two kinds of processing basically. One is melting casting. You have heard this obviously. We melt it and pour it and we'll get a solidified product. That is melting casting, right? You have to remember this. Melting casting is one of the processes. Another kind of processing is powder metallurgy basically. Powder metallurgy, where we produce powders of metals, then we can mix it, then we can compact it, we will get a pellet, then we can do sintering, and finally we will get an end product. So these are the major two processing route for metals and alloys. One is powder metallurgy, one is melting casting. Okay, very good. So forget about powder metallurgy right now. Consider only melting casting. Let me give, I want to make you understand this one. Suppose you are producing a metal or alloy by melting casting. Done, right? You have synthesized. Now the question is what kind of processing you can give, because you want to modify the structure. So what kind of processing we can give to a metal or alloy? You know that, I know. Okay, yeah. What kind of processing we are giving to a, okay fine, you have attended, fine, that's it. You people have attended the industrial visit, right? You have seen the cast products in the industry, ingots. Bloom, billets and all you have seen, right? Bloom, billet, slabs. Okay? How many of you have seen these bloom, billet, slabs? Oh, many of you know that, yeah. The bloom, billet, slabs, they are produced by pouring the molten metal in a mold and finally you get a bloom, billet or slab. They are difference in the dimension only. Someone is more longer, someone is more thicker and all. Dimension is different, but all are cast product. Okay. My question is, what kind of processing? You have also seen the processing, I know. You have seen hot rolling, cold rolling, right? You have seen, those are processing, no? Hot rolling and cold rolling, right? So that is actually nothing but the mechanical working. So one processing route is mechanical working, fine. I am giving an example of cold working, for example. Cold working is one of the processing. Okay. And the kind of processing where we are giving only thermal treatment. We just take the metal to high temperature, no, but below the melting point. Okay. Just we are providing heat, no mechanical working. That is actually heat treatment. We'll discuss that later, slowly. So one kind of processing can be mechanical processing, where you can give hot working, you can give cold working, or warm working is also there. It depends upon the temperature of the plastic deformation, right? And the processing is thermal treatment. Just heat the metal or alloy below the melting point and hold it for some time. Fine. So these are the two things. Other things may be thermomechanical working. That is very interesting. Thermomechanical working. Thermomechanical working means name itself saying thermal treatment will be given and mechanical treatment will be given simultaneously. Do you know that this rooftop? Those are iron rods, right? Iron bars or rods, whatever you can say. Those are produced by thermomechanical processing. The rods, which is the PCBs, for example. The PCBs those rods are made of by thermomechanical processing only. You have to remember, sometimes in interview they ask, the rods, the steel rods are made up of which process? You have to say it is made up by thermomechanical processing. That means thermal treatment is given and mechanical working, plastic deformation is also given simultaneously to give enhanced property. If you give thermal treatment, you will get a property. If you give mechanical treatment, it will give you some other properties. Okay, fine. So these are the things. Another kind of processing is very interesting. You people have heard about carburizing, maybe, I don't know. Maybe somewhere. Carburizing, nitriding, maybe. Those are basically done to automotive components. If you have a car, lot of the components of the car are given this kind of treatment. That is actually thermal and chemical, or you can say thermochemical treatment. Heat will be given, that means thermal treatment will be given, and some chemical will be also added. Like we are adding carbon into iron. Here carbon is the chemical. That is called carburizing, that's why. Nitriding means we are adding nitrogen and we are giving heat treatment. So it is nitriding. Some people call carbonitriding. That means carbon and nitrogen both will be given. Those are chemicals and thermal treatment is given. So these are the four things you have to remember. As I told, one is only thermal treatment, one is mechanical treatment, one is thermomechanical treatment, one is thermochemical treatment. Right? You can easily remember it. Fine. Okay. I can simply write. So linear relationship, how I can write? I can write processing cost, then structure. If you change the structure, then properties, then finally performance. Okay, fine. So this is the linear relationship between them. If you change this will change. If you change this will change. If you change this will change. So we want this one fine. Okay? Is it fine? If you have any doubts, you can ask me in the class itself. It's better. It may be silly doubt, no issue. Processing, structure, property, and performance. Okay. So as I told, can I erase? Okay, so now processing, you remember? What is? One is heat treatment, I can write. Then mechanical working. Then automechanical. And finally thermochemical. Okay, so these are the four things you can give. Different routes of processing. If you apply different processing, the structure will automatically change. Okay. Then, if I want to write the structure, two things: crystal structure and basically microstructure. These are the two structures basically. Structure may be also atomic structure, electronic structure, but we metallurgy people don't deal with that. No, chemistry people deals with electronic and atomic structure. We don't deal. Basically, we deal with this. That's why we use microscope always to check the structure. And to check the crystal structure, we use XRD, as I told, X-ray diffraction analysis. You people have done your internship in R&D. Maybe you might know this XRD, maybe. I'm not sure. Anyway, is it fine up to this? Crystal structure, you can see. Let me give a simple example. A very simple example. I am sure that you will get a question from this also. So remember this. I will take a piece of iron, for example. Now, I will take a piece of iron. Other, I will take a piece of steel. Better we are using steel, so better I will take a piece of steel. at room temperature, it is in which kind of phase basically? It is, just imagine it is basically having low percentage of carbon, very low percentage of carbon. Which phase will be there at the room temperature? Who is saying austenite? Ferrite. At room temperature, iron or steel exit in form of ferrite basically. That is body centered cubic. I talked about it is very low percentage of carbon. Ferrite. Okay, this is the body centered cubic. Now you do what? You take that piece of steel to high temperature, maybe around 950. So what will happen? It will convert into austenite, because steel is a substance which shows phase transformation. The phase will change if you change the temperature. Okay. So now material is same, that means composition is same, but now it is showing two different kind of crystal structure. One is body centered cubic, at high temperature it is phase centered cubic. Now, can you tell me, now you do some mind storming, I know you know the answer, do the mind storming and tell me which property will be changed now? Which kind of property? Strength, are you sure? Strength will be changed little bit, but both are ductile. Both are basically ductile. Austenite is also ductile, ferrite is also ductile. Both are ductile, basically. Magnetic property, okay, very good. Interesting. Magnetic property will change, of course, right? At high temperature, when it becomes FCC, it is non-magnetic. If you put a piece of magnet, it will not attract the magnet. So magnetic property will change. So that's why there is a temperature range called Curie temperature. The moment you take the iron to above Curie temperature, all the magnetism will get lost. It becomes non-magnetic, right? Okay. But ferrite BCC structure is highly magnetic. It will attract the magnet. Okay. So one very good one point is, you can see we have changed the structure. The property has changed. Magnetic property has changed, of course. Any other properties? Huh? Hardness. Okay, which one is more harder than you were saying? So somebody is saying hardness. Okay. Ferrite soft. It is very difficult to say, but hardness, the point is, if the material is at room temperature and having FCC structure, then you can compare, because temperature is different now. No? Conditions are different. See, if somebody is saying you want to compare the hardness, so your conditions should be same. The steel should be at room temperature only, you can measure the hardness, then you can compare it. But you are taking to high temperature. Once the metal will take into high temperature, its yield strength reduces, of course. Yes. No, yield strength will reduce means hardness will also reduce, of course. So how you can compare it? But if both are at room temperature. How many of you know that austenite also exists at room temperature? And what is the condition? Okay. That can still be remain in austenite phase at room temperature? Is it possible or not, and why? You people are very good in physical methods, I know it. Yeah. Okay, fine. Don't hide your face. Okay, you can answer it, I guess. Okay, how many of you people are agree that austenite will exit at room temperature also in steel? Please raise your hand. Okay, 50-50. Oh no, it's austenite phase can also exist at room temperature. That's why there is a concept called austenite stabilizer. Austenite stabilizer. You should remember this thing. Definitely they will ask this question in placement. What is austenite stabilizer? And many times question was there in GATE exam. Give an example of austenite stabilizer. Austenite stabilizer means, see, basically we know that austenite always exists at high temperature, above 910 or 912 degrees centigrade, right? But even if you can make a steel where austenite phase will be there at room temperature. How this is possible? Because lot of austenitic stabilizer element has been added to the steel. Lot of alloying element has been added, like manganese, carbon, nitrogen. These are austenite stabilizers. Carbon, nitrogen, manganese, nickel. You have to remember this for example. Carbon, nitrogen, manganese and nickel. What is the common between them? Can you tell me? Forget about, yeah. Forget about manganese. Manganese is HCP. But if you check nickel, crystal structure, and crystal structure of which one? Carbon 4 it is non-metal. Basically nickel, if you consider nickel is FCC and this iron austenite is also FCC. Right? Anyways, we will not discuss that right now. Anyway, you understood my point of what I mean to say? Fine? What was the question? I forget. I got diverted. Okay. That's forget. It is possible. Before that. Okay, yeah. That was my question. As he told, magnetic property will change. But any other property? Achha, you have studied this phase transformation? Yes. There is a phase transformation which occurs due to movement of atoms. That is called diffusion. You have studied that? Right? Now tell me, diffusivity property will remain same or it will become different? It will become different? Okay. So how many of you agree? Diffusivity you understood now. Migration of atom from one position to another position. That is called diffusion. More than one atomic distance maybe. So how many of you agree that diffusivity will change? Okay, many of you. Other people? Okay, can you able to answer it? How diffusivity will change? Delta? Delta T. What exactly delta T? You are saying something mathematics. Okay. Undercooling don't work here. Undercooling means when we are doing solidification, then undercooling works. Undercooling will not work. See, this question you will gonna get in the exam, I am saying, right? Again, I am saying you have a piece of steel. It contains low amount of carbon. At room temperature, the structure is BCC, and you have taken the steel to high temperature above 910. It becomes FCC. Now, what kind of property changes related to diffusion or diffusivity? So basically, diffusivity will be different. In which case diffusivity will be higher, and in which case diffusivity will be lower. See. If the structure is open, lot of space are available, diffusivity will be easy. Body centered cubic have very low packing efficiency. You remember the packing efficiency at least? Okay, very good. How much? 68%. And in BCC how much? And how much in FCC?
74.
74 and 68. And in normal simple cubic? 54. Okay, anyways, so you understood my point. So that means in case of austenite is a face-centered cubic structure. Its packing efficiency is more, right? So open space available is less. So diffusivity will be slow. You understood, or shall I write it? But in case of body-centered cubic is an open structure. Lot of available space are there. Why? Because its packing efficiency is very less. Understood? So atoms can easily move. So diffusivity will be higher. You need to maintain same temperature, but you can able to see that diffusion has happened well in case of body-centered cubic steel compared to your face-centered cubic steel. Shall I repeat or any confusion? This is a very interesting phenomenon. Okay, you understood? So you can see that property has changed, diffusivity property has changed because of different structure now, right? Similarly, can you tell me what happened to solubility? Solubility of carbon. Okay, very good. Solubility of carbon. What happens? Will the solubility of carbon will remain same, or somewhere will be more, or somewhere will be less? Where it will be less, where it will be more, or same? How many of you are saying it will remain same? Solubility of carbon. Okay, from the last bench here. Can you tell me if you add a little amount of carbon into iron, where this carbon atom goes basically? Where it will stay? Can you tell me? Yeah. Oh yeah, you are singer, right? Okay. You don't know? Okay, Chaudhary will say. Chaudhary, if you add a little amount of carbon into iron or steel, where it will go? You are saying something here. Oh, void, very good. Which void? Yeah, very right. Interstitial sites, very good. Yeah. Interstitial sites. Of course, interstitial sites. In body center cubic, where is the position of interstitial sites? Near to the diagonal position, close to the corner end and diagonal positions. Okay. In face center cubic, edge center, center of the edge and body center. You remember or you forget? These are very important points. During your MTech interview, sometimes they will ask to draw the face-centered cubic structure and ask you, show us the voids, where the position of voids are there. You have to show them. Maybe in interview they can ask sometimes. Simple questions, but you will forget it. Anyways, so my point is where solubility of carbon will be high and where solubility of carbon will be less. High temperature, okay, forget about, both are in room temperature now, tell me. This is a high heat. Are you sure? White. Your concepts are not good at all. Anybody remember the iron carbon phase diagram? You can check the position of those points actually. Can you draw it and see? Just draw the iron carbon diagram and just see. You will understand it. Yeah, draw it quickly. Yeah, already you have. Okay, very good. Now can you check and see what the solubility of carbon? The y-axis will show you the weight percentage of carbon, right? You can connect those points, then see and check. Ferrite, the position of ferrite is very small always, no? It's a very small. The bottom part of the iron carbon diagram, very small. Very small. So that means solubility is very less. See, material is same, your steel, but the solubility of carbon is less in case of body centered cubic. It has more open space, but still the solubility is less, but diffusivity is high. You understand my point? But in austenite, just see how much, 2.1 or something, at least. 2.13 or 2 point something, just check. We forget the position. Find 2.1 really, 2.13 or 2.1. So many people get confused. So you have to remember, whenever there will be an open structure, diffusibility will be high, right? But solubility, you cannot say it will be high. Some people get confused in this. Solubility depends upon the size of the voids or the position of the voids, actually, where the voids are present. Size of the voids and position of the void. Okay, maybe in the coming class we will discuss that in the details. Anyway, up to this it is fine. Crystal structure, microstructure. Then properties you can write. Properties means it may be physical property, it may be chemical property, it may be mechanical property. Yeah. Of course, ductility will be affected. Yeah, of course, it will affect it. Right. It depends on a lot of things. Actually, FCC has a lot of slip systems and all are active actually. All are active and good because the atoms are very close to one another in a particular direction and in a particular plane. So if you apply less amount of load also, you can easily move. Plaster deformation will be easy actually in case of. Anyways, austenite is very ductile, you have to remember. It's a phase which is very ductile. But again, it depends upon carbon also. If you add more carbon, it becomes more stronger, harder. Composition also matters. Anyways, property you understood, right? You can write the example also as I told. Magnetic property will change, diffusivity property will change, solubility property also changes, fine. And mechanical property depends upon many things actually. I am not talking about right now. But can you remember, okay, how many of you have seen my videos of physical metallurgy, at least first 2 lectures? Anybody have seen? Complete? Only you. First two lecture at least. There I have given an example of alumina, where you can change the structure of alumina and you can have different optical property. Optical property can also be changed if the processing will change. I will give one example. I have written my name and I have put that one. You haven't seen. Okay, let me give this example quickly. See, those videos are for you only. I am not going to earn anything. Those videos are for you. Just watch it. I haven't asked for like, subscribe and all. You can watch it, right? Even if I get money, I will share with you. Fine. That is the deal. Okay, fine. This is all are A2. See, this is the thing. All are same material, same size, same material, alumina only. A2 alumina. But if you check their optical property, it will be different. All are same material, same dimension, everything is same. But what is different? Just check. Microstructure, not crystal. Microstructure. First one is single crystal, that means no grain boundary. Second one, grains are there, means lot of grain boundaries are available. Third one, grain boundaries are available and some porosities are also there. So which one will show you the best performance if you want a transparent alumina? Single crystal, first one. You know that your this one tempered glass is made up of very high purity alumina. Your tempered glass is made up of high purity alumina, very highly pure alumina. I am not sure exactly it is single crystal or not, but I know it is high purity alumina. It's tougher also, tough. Anyways, see, material is same, but you have changed the structure. So which property has changed? The optical property. This is completely transparent, this will be little bit transparent, and this will be not transparent at all. Or this is completely transparent, this may not be transparent. Why this is happening? Okay, I want answer from you. Yeah. Why the first one is completely transparent, but second two are not? What may be the reason? Different process will affect the structure. Structure has been affected already, no? Now you don't know. Okay. It is visible. Just see. Oh yeah, you are saying something. Achha, do you know why the grain boundaries appears darker? And you have seen the grain boundary in the under microscope, right? Yes. Grain boundaries appears darker, basically. Darker and your the inside grain is somewhat appears brighter. Not white, I can say brighter. Why it is so? We use etchant, but I am talking about why it appears like that, darker and brighter. Somebody want to? Yeah. Okay. You are saying something? Yeah, you are saying something? Yeah, you may be wrong. Huh? We use etchant, but what happens if you use etchant? Then what will happen? Energy difference. So what will happen? Energy difference will be then nucleation. Don't give random answers. Carbon. Suppose I will take a piece of aluminium. I can able to see the grain boundary. Then no carbon is there, no, in aluminium. Then okay, how you can able to see me? I'm standing and how you can able to see me? Light is falling on me and going back into your eyes. Now reflection is happening. Okay. So same grain boundaries. That means grain boundaries looks darker because lot of light is not coming from that into your eyes. It is getting scattered. Light is falling on it, but it is getting scattered away from your eyes. But from the grain, inside the grain, lot of light is coming. That's why it is appearing as brighter. See, light is falling on this also. Here also grain boundaries, but grain boundaries will scatter the light. Why it will scatter the light? Because you have did etching, no? Chemical etching. The moment you are doing chemical etching, what will happen? Dissolution will happen. Some atoms will get dissolved along the grain boundaries. So it will become a void, valley. Suppose this is the grain boundary. Best example. This is a grain boundary. This is one grain. That is grain boundary. That is one grain. So light is easily reflecting back from this region, this region, this region. But if light will fall on here, they will scatter. It will fall here, it will get scattered to this. It will fall here, it will scatter like this. But it will not come back into your eyes, no? So that's why it appears as darker. So etching will help you to dissolve the atoms along the grain boundary. So why this is happening? Because as she told, because grain boundaries have high energy. So that will be get attacked by the acids easily. Because why? Again why? Reactivity, okay, not reactivity. Actually, again thermodynamics. Everything want to be stable, or everything want to reduce its free energy, right? So grain boundaries have more free energy all available, right? The moment you add acid, it will react with the grain boundaries atoms and it will dissolve, and some valleys will form. When the light will form, it will get scattered. That's why it appears darker. You cannot able to see easily. You understood my point? Okay, is it fine? Your concepts are not good. I don't know. You have attended the physical metrology lab also. Okay, anyways. Is it fine? You can see. So if you want to produce a single crystal, processing will be different. If you want to make a polycrystal, processing will be different. If you want to have porosity, processing will be different. So different processing, different structure, microstructure, different microstructure, optical property has been changed. So at least you can write these examples somewhere, or if somebody will ask. Is it fine? Last bench. But you will get a question on this FCC and BCC steel, how the property is changing, how the magnetic property is changing, how the your solubility, diffusibility, you have to explain it. Huh? Okay. Properties, okay. Performance you understand. It may be good, it may be poor, it depends. So that means this is a very good material having high performance, this is a very poor performing material. This is done. Different processing into property. I have told you different processing. These are, and okay, fine. We'll move to the important part. What is heat treatment and its cycles? And in the mid-sem, you're gonna get question from this also. What is heat treatment? And draw the cycle and explain it. Maybe. Very easy question. See. So this will be your temperature. This will be your time. These are the two axes. T is the temperature and small t is the time. So you may get a question. You may get a question. Draw a simple heat treatment plot or diagram. So y-axis will show you the temperature axis and x-axis will show you the time. These are the two important parameters. Time of the thermal treatment, temperature of the thermal treatment. As I told, heat treatment is nothing but it is the thermal treatment of the metals and alloys. We need to do heating, we need to do cooling, but the rate may be different. Sometimes high rate of heating, sometimes low rate of heating, sometimes high rate of cooling, sometimes low rate of cooling. So heat treatment in simple word means you are just heating the metal and cooling it. Actual combination of this, heating and cooling. But it may be of different rate. No need to remember the definition, just understand it. But it should be below melting point. You should not melt it. You should not melt it. And sometimes you should not go to very high temperature also, near to the melting point. What will happen? Can you tell me if we go to very high temperature, then suppose I will take a piece of steel and I am doing heat treatment, but I have taken to very high temperature below the melting point, but still high temperature. What may be happening there? You understood my question? Heat treatment means it is a thermal treatment. You are heating the steel, for example, but you are heating to a very high temperature, like above maybe around 1395 nearly. 1395 is very high temperature. or 1400 maybe. So what will happen? Grain coarsening may happen. Very good. We talked about now, right now. Heat treatment is a processing route, but now you have taken the metal to a very high temperature. So what will happen? The grain become very big. Coarsening of grain will happen. And if the grain become very big, what will happen to the property? It will reduce or improve or reduce. Which property will reduce? Strength. Very good. The strength will reduce. But if you want ductility, then it is good. It will improve. So that is the reason why hot working is done. You people have seen the hot working, no, in industry. Hot working plant, you have visited, right? Why they are doing hot working? Because they are taking the steel to or aluminum to high temperature. It becomes soft so that they can plastically deform it and make it very thin and very thin and very thin. Some micron size maybe. From 600 mm to micron, you can understand. Below this, they can make it. From this much size, from here to here, then they can make it like this. Why? Because at high temperature ductility is very high. Right? Grain become coarser, that's why. It's Hall-Page relationship. I don't know if you people know this or not. Maybe we will discuss that somewhere. Is it fine? So now you can draw it. This is 1, this is 2, and this is 3. So this is your cycle 1, this is your cycle 2, this is cycle 3. So heat treatment have 3 different cycles. Whenever somebody will talk about heat treatment, that means it will involve 3 cycles. They are continuous. One is called heating cycle, second one is called holding, and third one is called cooling cycle. This is the one is and third one is. So as I told, heat treatment is nothing but it is a thermal treatment of metals which involves heating and cooling of metals. Simply. No need to remember the definition, just understand. And she told somewhere, right? This holding cycle is also called soaking. In metallurgical terms, it is called soaking. Soaking means what? Holding. That means they hold that metal or particular steel or aluminium or copper, whatever, for a certain interval of time, so that it will absorb more amount of heat and the temperature will be uniform. The question may be like this: why we have a soaking cycle in heat treatment? So what will write? Why we have a soaking cycle? I can go like this, for example. I can draw a diagram where I can draw this like. I can draw this. So there is no soaking cycle, no holding cycle. See the second diagram. No. Fine. So what is the need of soaking? Uniform, yeah. To make the temperature uniform everywhere. Because the moment you expose the metal to high temperature, the surface will be getting heated up at a fast rate. But what happened to the core or at the center portion? The center portion or the core is not exposed to the heat. Slowly heat will transfer from the surface to inside. It takes some time. If the dimension of the metal is very big, then soaking cycle will be also more. So soaking cycle will be depending upon the thickness. In other ways, simple. It depends upon the thickness of metal or the alloy. If you have a very thick metal or alloy, soaking cycle will be more. You have to give more time for soaking or holding. You have to remember that. Why? Because you want the heat should be uniformly present everywhere. Or in other way, I can say temperature should be same everywhere. Suppose you want to do soaking at 1000 degrees centigrade. Let it be 1000 degrees. So maybe if you measure after half an hour, maybe core temperature will be somewhat 700 degrees centigrade, but surface temperature will be 1000. So it is not proper. The core should be at 1000 and surface should be also at 1000. Then that is soaking cycle is done. Then you can go for cooling cycle. And the important point you have to remember, soaking cycle also depend upon the composition of the metal or alloy. Suppose you have a pure iron, let it be, and you have a highly alloyed steel. So in which case you need more soaking cycle? High alloy steel, very good. Why? You are right. You are right. A lot of alloying elements are there. Those alloying elements has to move. Those alloying elements has to move, diffuse. So diffusion depends upon time also. Also depend upon temperature. Exponentially depend upon temperature. Time also matters. So if you have lot of alloying elements, then soaking cycle will be more. But if it is a pure metal, soaking cycle will be very less. Or if it is lightly alloyed, soaking cycle also get reduced again. Another important point, soaking cycle also depend upon what kind of alloying elements are present. It depends upon the amount of alloying elements, also depend upon what kind. Suppose carbon is present and vanadium is present. Vanadium, niobium, you know these things are added in the steel. Any idea from physical metallurgy? Okay. Niobium, vanadium. We add vanadium and niobium into the steel. For what? Why we do alloying addition? To strengthen the metal, to increase the strength. Yeah, very good. So what vanadium and niobium do? Yeah, carbide forming elements. Very good. He knows that. Vanadium form very strong carbides. Vanadium carbide, niobium carbides. Sometimes they may form nitrides maybe, but most probably carbides they form. So carbides means what? There are precipitates actually. Carbides, nitrides, they are precipitates. And if precipitates will be there, what will happen? Precipitation strengthening will happen. No, that is one of the mechanisms, precipitation strengthening. You have studied this in deformation behavior, I guess. I'm not sure. Anyways, so if vanadium, niobium, those are actually heavy elements. You can check the periodic table, see the positions. Those are heavy elements actually. Vanadium, niobium are very heavy elements. The mass is very high. So what will happen? They cannot diffuse at very fast rate. They will diffuse very slowly because they are heavy already, no? Bulky. But carbon, the weight of carbon is very small. The size of carbon is very small also. It can diffuse at a very fast rate. So diffusivity depends upon the weight also now, or mass of the elements. So I mean to say is, soaking cycle depend upon one point, it depends upon the thickness, it depends upon the amount of alloying elements, it also depends upon what kind of alloying elements. These are the 3 points. You can write some example if you want. If carbon will be there, then diffusivity will be fast, soaking time will be less. If vanadium niobium will be there, soaking time will be more, because it takes more time to diffuse or to homogenize. Technically we people call homogenization. In metallurgical term, homogenize. Homogenization means in terms of temperature, in terms of composition. You have to remember. Whenever somebody will ask homogenization, you have to say in terms of temperature. That means temperature is same everywhere. Wherever you take a metal piece, it will be same. And composition also. Same amount of vanadium should be present everywhere. Same amount of carbon should be present everywhere. That is homogenized condition. Okay. Up to this it is clear, I guess. Or you have any question, you can ask me. And the most important part is this cycle. This is the cycle which will decide your property mainly. See, soaking you have to do anyhow. Anyhow you have to do soaking to get uniform temperature, to get uniform composition, right? But cooling cycle will decide the final property. Whether it will be ductile, whether it will be very strong, or whether it will be tough. Whatever the mechanical properties you know, ductility, toughness, and your yield strength, tensile strength, or impact strength, whatever mechanical properties you know, creep also. So mostly it is affected by this cooling cycle. It doesn't mean that this cycle is not important. This is important, but this will affect a lot of problems. Cooling. So heat treatment involves heating cycle, soaking cycle, and cooling cycle. Fine. And another important point you have to remember, this heating rate is also different. You can change the heating rate. You can go for slow heating rate, you can go for very fast heating rate or medium heating rate. It also affects sometimes. Similarly, as I told, cooling rate also different. Can you draw different cooling cycles? Slow to fast. Just draw it. Different heat treatment cycles showing different cooling rate. Yeah, you know that. Yeah, you draw it. At least 4 cycles can you draw, showing different cooling rates. Different cooling rates. 4 cycles, different cooling rates. Just use your mind at least, na? Then I will tell you. Different cooling rates. Cooling rate will be different. Fix the heating rate same, but cooling rate will be different. You draw it? Yeah. In one single cycle, it is fine. In one single cycle also you can show. No issue. See, I can do like this also. I can do like this. I can do like this. So this is 1, this is 2, so this is 3. Different 4 cooling cycles. So which one is the fast cooling? The one is very fast. Then slow 2, then slow 3, then finally very slow is 4. And technically this is called quenching. Very rapid rate of cooling. We'll discuss that in coming lectures. That's what quenching. How it is done? Just take out the sample and put it into the water, or maybe ice, or maybe salt water, brine solution, or maybe oil, whatever. So you are putting the sample from high temperature into oil, into water, into brine solution, and into, for example, a room temperature. So different processing, and you can check the hardness, simple hardness. Everywhere it will be somewhat different. You understood my point now? Simple, you change the processing. Air cooling, water cooling, oil cooling, then brine cooling. Everywhere if you measure the hardness, measure the strength, it will be different. So final conclusion is what? If we change the processing, simple processing can change the property. And heat treatment is one of the important processing route where we can change our property. This is the final conclusion of today's class. And heat treatment is very easy to do also. You don't have to do any kind of mechanical working. Your father will give a piece of metal and ask you that can you change the property without doing anything. Just take it and heat it. After some time, and heat it and pour it into water. And take another metal and just cool it in air. You measure the hardness. Where you have put it in water, the strength will be high or hard, it will be more harder. Air cooling will be not showing very good hardness and strength. So that means heat treatment is very easy to do. That's why in industry also they are doing heat treatment. Very easy to do. No need to deform it, no need to add any chemicals. Only just heat and cool. But you have to remember, heat treatment is mostly given to those alloys or those metals which shows phase transformation behavior. Basically, not always anything, basically. If you want to improve the property by doing heat treatment, you cannot do heat treatment to any kind of metals and alloys. Suppose I will take a piece of pure aluminium now. Let it be pure aluminium. And I will do heat treatment on it. Do you think that it will show different behavior? Not, it may show different behavior but not significant. Not significant behavior. But if you take a steel or iron, you heat it and cool it, it will show different behavior. Why? Because crystal structure will change in case of iron or steel. You take a piece of copper and do heat treatment on it. Do you think that property will change significantly? No. Copper, if you take the copper to high temperature, it will remain at FCC. Room temperature also FCC. Even if after fast rate of cooling also FCC. Every time FCC will be there. So crystal structure is not changing. So property will not change. Take a piece of aluminium, heat it to high temperature. Room temperature aluminium is FCC. High temperature also it is FCC. You cool it at different rate also. It remains FCC always. Slow or fast or anything. Because crystal structure is not changing. If crystal structure will not change, the property will not change. It will change, but it will be not significant, I think. Whatever you want, it will not be there. Little bit change will be there. Of course. Why? Because grain size may change. If small grain will be there, then maybe some strength will increase, hardness will increase. If grain size will be big, strength and hardness will reduce. but that is not will be significant. But steel, iron always show phase transformation behavior. It remain in BCC, sometimes it remain in FCC, sometimes it remain in BCT also. Martensite. Body center tube. Martensite is very hard, na? Right? If you take a piece of steel and quench it, you will end up with martensite. And martensite is body center cubic structure. It is very hard and brittle. But if you cool it, suppose you cool it like this, you will end up with which crystal structure? Maybe body center cubic, simple body center cubic. Right? So that's why heat treatment is always easy to do, and you can easily change the crystal structure, or you can easily change the microstructure, so that you can get the better performance or better property. Okay, fine. Any question you have? Can you ask me a single question at least from today's class? Any random question? Fine.
Sir,
Yeah.
so the first one you said is quenching, the fourth one is probably annealing.
The last one is annealing. Yeah, you can say.
So what are the second and third? One is normalizing.
And the one is, it depends upon the, okay, fine. It depends upon, for example,
Some fans or something.
exactly. It depends upon, like, for example, you are taking it out to the room temperature simply, right? The cooling rate will be one time, but if you take it out and allow some air to flow on it, so it is forced cooling.
Yes.
Fine. Okay, fine. Can you?